Welcome to this episode of Yugabyte Friday Tech Talks by Engineers for Engineers. Hope you're all having a good day. Uh, I'm Sanketh, Technical Director at Yugabyte. I work on the Kubernetes support for Yugabyte and the Yugabyte Anywhere control plane. And today we have with us Aman. He's a senior engineer at Yugabyte D. He also works on Kubernetes support for Yugabyte and the control plane. And he's here to share more details on the newly released Yugabyte DB operator for Kubernetes. So hope you guys will all enjoy it. Over to you, Aman.
Thank you, Sanketh. Yeah, hi. Sanketh, I'm Aman. I work on the Yugabyte Anywhere team. Today we are going to talk about the Yugabyte Kubernetes operator. It's a new Kubernetes operator that we have built to manage Yugabyte DB efficiently on Kubernetes. So here's the agenda for today. So we'll discuss what's the current landscape and what are the options for managing Yugabyte DB. What are some of the trade-offs when we use, like one of the options is Helm charts. So what are some of the trade-offs when we use Helm charts? And then some of the also complexity associated with managing distributed databases on Kubernetes. And then we transition over to Yugabyte DB operator demo and discussion of the features, and then discuss operator architecture, future plans, and how to contribute for the users. And we also have time for question and answer at the end. And also if there's questions in the middle, we can ask and answer them. So when we talk about Yugabyte DB on Kubernetes, right, what is the current landscape and how to manage it, right? So on the OSS side, we have Helm charts, right? And on the enterprise side, we have Yugabyte Anywhere. Yugabyte Anywhere is, an enterprise solution. It's production grade, full DB lifecycle management across many different substrates. It has extensive validation and safety checking for included observability and alerting. It is full featured on the enterprise side. On the OSS side, we have what available today is Helm charts. Helm charts allow for single AZ, multi-AZ OSS Kubernetes management. They're production grade. We have them in production for a few years now. The multi-AZ support is slightly limited. I mean, you can manage multi-AZ clusters, and we'll go into some of the details on how to do that and why it's complex. And then similarly for multi-region, some of the same limitations hold. Primary operation for the Helm charts is using Helm CLI, and primary operation for the YBA is using YBA API and UI. Also sort of figuring out what is what is the sort of challenges when we use Helm charts today, right? So some of the challenges, one, because we use the Helm CLI, things tend to become non-declarative because not everything can be expressed in as part of the Kubernetes YAMLs. To do a multi-AZ cluster using Helm, we basically need to deploy 3 copies of the Helm chart with synchronized values.yamls across AZ. In each of the values.yaml, we have to add placement info. We have to pre-compute some master addresses, which are some other configuration for the database. It's also not easy to horizontally scale just using a Helm chart. And the reason being, basically, when we have to, for example, when we are scaling down, and we'll go into some more details as well. But when we are scaling down, we have to also consider the health of the database, respect the replication factor. And all of these need to be done outside the Helm command itself, and which makes the whole process a little bit non-declarative, right? Another key area where Helm charts don't work is backups. So if you want to take backups, today the option on Yugabyte DB with Helm charts is to run in YSQL dump and then move the YSQL dump over to some background object store or external storage, right? And that requires some credential management. It also doesn't allow us to use the efficient database provided snapshot APIs. So that is another sort of point there. So just to sort of look at why multi-AZ charts become hard to manage using Helm. So here's the state machine of what we need to do to even just create a multi-AZ, right? So we have to first have all of the prerequisites satisfied. So we have to have a storage class that has wait for first consumer. Then we have to do 3 copies or n copies of the Helm chart, each copy with its own values.yaml. And then in each values.yaml, we have to pre-compute some addresses of the YB master, and then also pre-compute placement info. Like for example, each values.yaml will have like, this is for this AZ, this is for this region, and so all of that needs to be
So
managed outside of Helm.
the pre-computation is because your each AZ has one master, and then you have to inform that master about the other master, right?
Yes. So each AZ has one master and a number of T servers, and you have to inform each of those pods about the other AZ. And because they're not part, like they're each of them are separately managed stateful sets, we have to pre-compute all of that information so those pods can, when they come up, they can find each other basically, right, and discover each other. And basically, once we deploy these Helm charts, then we have to wait for cluster creation, which is some amount of time for this discovery process to go through. So pods come up, talk to the masters, which are in special mode, and then create the database cluster and have the universe ready. Then once the universe is ready, we have to verify that everything looks good. So we run some basic queries against it. And then what we also have to do is configure the universe. Now the universe came up, but it's not aware that it's now multi-AZ, right? So we have to run some extra commands using IB-admin to configure that now this is a multi-AZ cluster, and each AZ, we have to run some commands to say, that this particular T server is part of this AZ, basically. And that is sort of zone-aware replica placement. And then once that is done, we then have to deploy, if external clients want to talk to the database, we have to deploy, a global service for how the external clients can reach us, right? And that's sort of, and then at that point we call it done. So as you can see, right, it's not, so we're doing a combination of Helm and then running commands outside. It's not completely just, just managing Kubernetes resources. So it's not a very declarative, completely declarative process, right? So, and so that was, day 0, just starting a cluster. Right? Now, let's say we have a cluster up and running. We still have to manage some lifecycle operations, right? So, let's say, a good example would be we have to set G flags, which are some configuration options for the database. We have to scale the cluster down because, let's say, we provisioned a large cluster. Change the volume size. Maybe we want to scale the number of nodes down, but increase the volume size, right? Those kind of are common operations, right? And then a new version of Yugabyte DB is released, so we want to do a software update, right? So today, if we want to do this in Helm, the way to do that is sort of the state machine on the right, right? So we start, pick a predetermined order of operations. So maybe we'll do the scale down first, then set the configuration, right, then volume. So we have to predetermine, and for each of these operations, then we have to launch, and we have to track their status to failure or success, right? And if they fail, then we have to take care of retrying them. Not all operations, could be retryable at each point in time. So we have to manually validate some state to make sure that we can easily retry the operation. For example, changing volume size is another tricky operation because we manage pods using stateful sets. Changing volume sizes are not easy because the pod spec itself is immutable. So we have to, basically create pods in orphan mode and then retry the stateful set creation. So that's a complex process that has to be done like outside of Helm as well. So it becomes pretty complex to sort of manage lifecycle operations, at scale. So as opposed to, if we use a Kubernetes operator or declarative style, right? What we would end up doing is basically set the desired state. So you can say, we want X version of Yugabyte DB, we want, certain volume size, we want certain number of nodes, and then periodically just check the status to see if, what is the status of whatever spec we set declaratively, is it done or not, right? So compared to the last slide, like this is much simpler for users, also much simpler to track, and it also takes a lot of the guesswork about like retrying out of the picture. And so here, all of that complexity is done by the Kubernetes operator, right? So it would check status of the resource to see if it is done, and figure out what is the right order in which to execute the operations, right? So here's how it would look, how sort of generally declarative style would look like. So there's a custom resource. We will have a version, and the spec basically controls what we can set. So for example, here num nodes controls the number of T servers. And we can set various kind of like we can set the software version of the Yugabyte DB. We can set other various properties and basically depend on the operator to then create the universe correctly. It also gives us repeatability, right? So if you want to create some, for example, a test bed, we can always be sure that we are creating the same kind of cluster in the same manner. So that
And
is the
like I
other.
guess so like typical Kubernetes, can any all these fields could I edit them to do what I want to make the changes, or like
Yeah.
the
So
changes that you described, volume size, scaling up and down, so those correspond to editing these fields, I guess.
yes. So for creation, we allow changing all of the fields in the spec. And just like stateful set or some of the other Kubernetes resources, some parts of the spec are create only, and some parts of the spec are mutable. So in our case, that is also true. For example, load balancer, enable load balancer would be one field that is not that is not mutable, so that is immutable. Replication factor is also immutable on our end. So so there are some fields that are, and for example, on volume size, we can only go up, because reducing the size of the volume is not supported. So there are some limitations, and we also encode all of the limitations into the validation that we do. So, for example, if we try to edit a field that's non-editable, we don't even accept the operation. So we have extensive validation rules expressed in CEL that are sort of will not allow us to update fields that are not editable. So this is same as what Kubernetes does for its some of its own resources as well. So yeah.
So CL is a
Um,
relatively new feature of Kubernetes, is it?
Yeah, so CL is a common expression language. It's I think it came out with 1.27. So prior to CL, in order to
You
validate,
need
you need to write webhooks to validate inputs to the custom resources. And with CL, that can be expressed in the CRD itself. So it has a almost like an open API v3 schema that we can use to express what are the valid inputs for a CR for a particular CRD. So
Oh, got it. So
we
it's
use
all
that.
part of the custom resource definition itself, the
Yes,
validation.
yes,
Got
yes, yes. So yeah, so just at this point, so we kind of went through what are the challenges of the Helm chart managing Yugabyte DB on Kubernetes. And we also saw some of the trade-offs, what things operators make easy, right? And also another thing, with operators is that it's easier to integrate with other aspects of Kubernetes as well, because in sort of ideal operation, we don't want to sort of in production, we don't want to have imperative operations sort of changing the cluster. And so operators generally are an easier way to manage stateful workloads, in production at scale. So, and yeah, so yeah, so basically going to what is a Kubernetes operator? Like also we've been talking sort of about it, right? So what are the various parts of a Kubernetes operator, right? So there is operator typically have three parts, right? There's a custom resource which is sort of describing the state of the underlying resources that are being managed. There's a custom resource definition that describes the schema that we talked about, right? So the schema of the custom resource. So what fields are supported, what are editable, what things can be changed, and so on, right? So that is defined in the custom resource definition. So custom resource definition can be assumed as sort of an extension to the Kubernetes API, right? So basically, we are teaching Kubernetes API server about some new resources that it can now manage. And then the third part is the controller. Controller is sort of the business logic of how the spec is basically turned into actual reality, right? So mostly it follows the controller pattern, where the controller watches for custom resources to be created or edited, and then the API server will give us events to the controller, basically based on if a new resource is created. It's following the edge trigger pattern, so you get the event, and then as it happens, and then once the event happens, then the controller takes care of figuring out what kind of event it is, and then taking a diff between the actual state of the system on the Kubernetes cluster and then figuring out a list of operations that need to be handled to realize the new changes that the user wants us to do. So that's sort of the high level. In For our case, we have one controller, but for every sort of custom resource that we manage, there can be controllers that manage multiple custom resources as well. But for our use case, generally we have one controller per custom resource that we manage. So at this point, we want to show like a quick demo of how how easy it is to install the Kubernetes operator and then get a Yugabyte DB universe running on a Kubernetes cluster. So the next few slides will go through like setting up prereqs. There's also a QR code here, so to the README file on the Kubernetes operator repo if viewers want to follow along and do this. So there's some prereqs. So we need help to install the Kubernetes operator. We need some resources. So for the operator itself, so we recommend 1 core and then 2 gigs of memory. As described, like CEL is used to validate the CR input. So we need a Kubernetes version 1.27 plus cluster. And then we also need RBAC, right? So so operators and CRDs are privileged resources on Kubernetes cluster. Also, so we need a service account that is allowed to create cluster roles, that is allowed to install CRDs in the cluster. And in the current demo, the operator will create it by default, but this is something that's needed. Also, if we are using Minikube, we sort of need a 4, we validated this configuration. We need 4 CPUs and 8 gigs of memory to successfully bring up the operator and a universe with 1 node of master and T server each. And we also need these labels. So the operator automatically determines the number of AZs in the Kubernetes cluster based on the labels on the nodes in the Kubernetes cluster. And basically, to sort of continue with that functionality, we need these labels. And these are standard labels. So which
do we need those labels even if we're creating a single AZ cluster, or do we only need them for the AZ cluster?
Yeah. So today, like in the code, the way the code is written, we need that even for single AZ because to create the provider. But yeah, you're right. We in future we don't really need them for a single AZ cluster as long as they're all. We can basically assume that if these labels are absent, we are in a single AZ cluster. Yeah.
Got it. And usually, would these labels already be present on like a GK cluster or a EKS cluster, or I would still need to add them manually?
Yeah, these are standard labels on nodes. So on GKE and EKS clusters, they're present. For some reason, they're not present on Minikube in the version that we tested with. But yeah, these are present on cloud provider managed Kubernetes cluster.
I had one more question on the RBAC on the previous slide. So the RBAC, roughly what are we granting to this service account? Like the cluster roles, roughly what do they allow?
So we need so we do cluster roles to be able to create new service accounts. We also need, in some cases, to actually the way we do this in operator, technically we could, as long as we have the namespace admin, we're good because we deploy all of the resources in a single namespace. But yeah, and so those are sort of so the ability to create service account. Then also we have some get permission on nodes to get the labels. It's all clear. It's actually all pretty well documented in the Kubernetes operator repo. Like if you look at the RBAC, there is RBAC.yaml. If you look at, we go through exactly what is needed there.
Got it. So I guess my question was like the roles itself, are they, so I think you mentioned here it's on a particular namespace. So if I have namespace admin, I'm good on that namespace, and the database cluster,
Yeah,
sort of everything works within that namespace.
yeah. So the way we deploy the custom resources as well as all of the resources for the universe is by, so we have two modes for the operator. There's one namespace mode and the other one is cluster mode. So if we say, if we use it in the namespace mode, it means that the operator will listen on a specific namespace for a CR to be created. And then all of the service resources that get created for the universe then get created inside that namespace itself. So you're right. So if you have namespace admin in namespace mode, we are good. But if we are using the operator in the cluster mode, then the operator can listen to all namespaces, and then basically in each namespace, wherever the CR is created, it will create the subsequent uh, uh, Kubernetes resources, right? So it's more efficient to usually run in the namespace mode, and also, so if you're using it for testing, more than one instance of the operator can be used to test. And it also contains everything in a single namespace, and yeah, like the amount of privileges required are reduced. However, installing CRDs itself is a privileged operation, so those are cluster level resources, so
We'll
those need
need
to,
a cluster
you
admin
need a
for
cluster. Yeah,
people and
so for those, yes. uh,
makes sense. Thanks.
yeah. uh, So let's see. I think yeah. So this is the first demo. So we'll go through this. Like this will show how the operator is installed and how to then use the YB Universe custom resource to deploy a universe there. So the first step is just cloning the Yugabyte K8s repo, installing the CRDs. Once the CRDs are installed, we basically deploy a bundled Helm chart. That Helm chart is bundled in the Kubernetes operator repo. And so that is just done using regular Helm command. So yeah, so we first create the namespace in which we need to install this. So we are creating this operator in the namespace mode. And yeah, so that's the command to run. As you can see, that's the command to run the operator installation. And the RBAC that we talked about, like there's a values, that top level value that controls creation of RBAC. So if we set that to true, then we create appropriate service account and cluster roles that are needed for the operator. Yeah, and then once the operator is, once the resources come up, we also run some jobs to make sure that the operator is available to then start serving queries. So we do that as part of a Helm post install hook, and that's basically what's running. So it waits for the operator to come up. So it will fail a few times before it starts.
Just a time check, Aman. We are sort of 7 minutes away from the 30-minute mark.
Okay. Yeah. So at this point, operator is up. A Helm install goes through. The operator is up. So we can look at basically now this is we have predetermined some, we have pre-built some CR. So this next step is installing some of the custom resources to bring up the universe. So you can see that we're just doing a kubectl apply for the custom resource. And this is how we also went over it before, but this is how YB Universe custom resource looks like. Yeah, and so we can see, the resource got created, and basically, if we do a get on the resource, we can see it's in creating state. Once that state finishes, once the resource, all of the resources for the universe have been deployed, it turns itself to ready state. So yeah. And also, as we are going through creation of this universe, we publish events to keep track of what is the current process that's going through, and they're all in the same namespace, so they get sort of interleaved with any of the Kubernetes events as well. So if you do a get events in that namespace, you can see what's going on. Here we can see all of the pods for the database universe are deployed. And yeah, status is still creating. So yeah, so next part is just watching for the status to be created. You can probably move a little bit further.
And this is a multi-AZ universe, right? So all that coordination steps that you showed before, They're all sort of
Yes,
silently are they happening under the hood,
they're happening
kind of.
under the hood. The operator is taking care of doing that. Yeah. And you can see once the universe gets deployed, all of the CQL and SQL endpoints get logged. So the first three are for the internal cluster, and then for the load balancer if you want to expose the service outside. And you can see once the universe was deployed, the actions become empty. That there's no more action right now, and the status becomes ready. So that's sort of it's how we could get um, quickly get up and running and try out a basic DB universe with using the operator. Right? So we saw how easy it is to install and create. But here is a list of features that we support for the operator today. Right? So on day 0, we have multi-AZ, single-AZ universe creation, backups and restores that are available. We also have there's a second demo that we'll quickly go to. We also have an inbuilt observability UI that will show as part of the universe that gets deployed. Day 1, we support horizontally, vertically scaling, updating volume sizes, pod scheduling, updating the pod scheduling. And then day 2, we also have log collection using support bundle. And operator itself can be upgraded using HAM. So yeah, just to sort of quickly demonstrate what we saw, right? So there is a what is going on basically when we create the universe, right? So kubectl, when we do a kubectl create, the custom resource gets a notification, basically goes into state creating. Our operator reconciler gets a notification to say new resource has been created. It queues up a task and adds some context on that background task to say, this is the CR that asked for the creation. These background tasks are then run to execute the universe creation, and basically it can either fail, and if it fails, then it's automatically retried, and if it is success, then the custom resource status is set to created already. Right. So that's how we handle create, and this is what we are doing like on the cluster itself, or what we are deploying. So we have we're deploying 2 main stateful sets, one for YB master, which is the sort of database control plane, and then one for the T server, which is handling all of the user traffic and Postgres traffic as well. So, and then we have PVCs associated with each stateful set. And in a multi-AZ case, there would be like n number of stateful sets for each of master and T server. For admin clients and app clients, we have that are inside the cluster. We have a headless service that points to the stateful set. For clients that are outside the cluster, we have we can create load balance services out of band. And by the way, this is something we'll also change in the near future. We'll add a ability to create, like in a multi-AZ scenario, ability to create like a global service across all instances of T server and master. So at a high level, like this is the architecture of the operator. So as I said, like for every custom resource, we have a reconciler. So for example, for backups, restores, by the universe, there is a reconciler that watches the custom resource creation in the Kubernetes control plane. As soon as there are notifications, it will basically react to the notifications, do a diff operation between the current state and the spec, and create Kubernetes resources on the fly. And then once all of those users are created and are in the correct state, then it responds to the control plane to basically add change the status of the resource. So similar to create, like this is also a state machine for how the updates are handled. So basically, the thing to sort of focus on here is that a lot of these operations are done in background manner by the operator. So, and we also don't poll for these operations. Basically, the way this is implemented is that when the background operations are launched, we persist enough context on the background operations to know which basically CR launched them. And so there is no polling. So basically, we only use the CR itself to for any of the control path signaling to for failure and retry. So if
Can
an
you also
operation
give
fails, you
some?
can.
Yeah. Can you also give a taste of like what goes on? For example, a scale down. You showed a pod architecture. Is it just scaling down those pods? Like, is it deleting pods? What goes on generally for an operation like scale down, for example?
Yeah, so it's not. It's not just scale down of pods. So, for example, even in a single AZ, which is the simplest scenario, right? If you want to scale down, There is, so we cannot just take the pods down it because we have to respect the replication factor that is set by DB, right? So what we have to do is we have to evacuate the pod. So let's say customer wants to scale down pods, right? So we have to evacuate the pods, move the data off of those pods, assuming it's only a T service scale down, so like not some easy move operation, right? So evacuate, we have to then wait for the data to completely move off of the pod so it's empty, and then only we can actually remove the pod, right? And then once we do that, we have to make sure cluster is in a healthy state post that removal, right? If any of these steps fail, we have to then retry the operation. So as you can see, it's not like just this, like scaling down the number of replicas of the stateful set, right? There is other operations involved because it's a distributed database to manage
So DB
safety.
level RPCs or something. Okay, makes sense.
Yes, yes. So there's a second demo here. So let me quickly start. So there's three smaller demos that are part of this one. So one, we show the advanced retry capabilities of the operator. The second one, we show sort of an end-to-end example of how the client and the observability UI and how we can sort of make changes while things keep running in the backend. And then the third one, if you have time, we can also go over some of the backup and restore it. So you can see that, so this is the same custom resource that we've seen before. So we just create a universe on the left. On the right, we will be looking at, what is going on in the backend. So if you notice carefully, actually, we started the universe creation. We look at pods in that same namespace. We can see that pods are in pending state. So we'll see why they are in pending state. So we do a describe on the pods, and we can check that basically, pods are not getting scheduled because they cannot find the right nodes to get scheduled. The reason for that is because we added a node selector in the override YAML. I think the video kind of moved quickly over that. But basically, we realized that we don't have a node selector that we added. And on the left pane also, we can see that the universe goes in error creating state, and then it automatically retries, right? And then as soon as we add the label that we need workload equal Yugabyte on our nodes. So, sorry. I think I pressed the. Yeah, so you can see that we have that node selector. So yeah, and that was failing scheduling. So as soon as we add, we can see on the left it goes into error creating. As soon as we add the label, so what we can see is the task on the left gets retried, and then when we look at the pod status, we'll quickly see them basically being redeployed and then going into running state. Right? So yeah, they're now in running state, and then we'll see on the left pane once they're in running state. Yeah, eventually the universe goes to ready state. This is the second part of the demo, and here I can describe what's going on. So on the top pane is basically the universe that we just created. On the middle pane here is a client that is constantly running workload on the universe. On the bottom plane is a global service that we created for our observability UI and also a service for each of the T-server pods. And on the right here is this inbuilt observability UI that is part of any universe that's deployed by the operator. This is our Yugabyte UI. It's a read-only UI. It allows us to visualize some key metrics, also look at what is going on with the cluster in a UI, right? So yeah, so we can see basically what's happening. What we're going to do now is increase while we are running this. We'll increase the number of nodes in the cluster, and we can see some of the key metrics here: live nodes, operations per second, latency for each of the operations. So just increasing the number of nodes is quite easy. We do a kubectl edit on our resource. We find the num nodes. We increase it from 3 to 6. So now, from being one node in each AZ, now we have 2 nodes in each AZ. And then we wait for. So right now, operator is running some validations. We can see once the validation complete, it goes from ready to editing state. And we can check the status of the cluster. It shows still 3 nodes. Once you refresh the page, it goes from 3 to 6 nodes. And we can see the new nodes are coming up and starting to take traffic and then starting to also take tablets. Eventually, once the post checks for the operation are complete, the resource state is going to move back into ready. You can see the whole time we were doing this, like the client kept running and talking to all of the resources there. Right? So now we see universe is in ready state. Most new nodes have come up, so there is a T server 0 and a T server 1 in each AC, and you can see the number of tablets are balanced on each of those. It's taking connections, so this is instantly functional, right? And all we needed to do was just to bump up the nodes, and the same holds for scale down as well. So yeah, this is the third part of the demo. It shows how easy it is to take backups using the operator as well. So we have something called a storage config, which basically is a wrapper custom resource for managing credentials to backend object stores. So that's called a storage config. There's a custom resource for that. So we create that one. And then basically we have a universe that we created. So there is, we can see that there is two databases on it. There's Postgres. So we want to take a backup of the Postgres key space. So the way to do that is by creating this backup custom resource. So we create the backup custom resource. And we name it, and then basically, just like any other custom resource, we do an apply. And once we do an apply, we can see, what are the current backups available. So we can see, as soon as we did an apply, the backup changed to schedule, and then once the backup got completed, the backup state got completed, right? So we can see like
Where were you would have needed to specify something like the S3 credentials. I think those were already, was it part of the backup resource or?
Yeah, so when we check the back, actually, let me back this up a little bit, maybe when we are going through I moved quite fast. So basically, when you look at the backup spec, right? So there is a backup type. So we are running a SQL backup. There's a key space which is basically pointing to the database. There is a storage config reference that we talked about earlier, right? So that storage config is what encapsulates all of the backend object store credentials, right? So you just need to create it once, and then any number of backups can use it. So not every backup has to have managed that separately.
So, and is it a separate CR, or is it a sort of a secret file that we have to create?
So it's a separate custom resource today. In future versions, what we want to do is also use these credentials like to get it from a existing Kubernetes defined secret as well. So so the backup quickly goes from. I mean, this is a little bit sped up, but it's quite fast. The backup quickly goes from schedule to done. Similarly, we have once you have a backup, you want to also restore it. So the restores works in the same way. We create a restore job CR. You can see, basically it goes like in the restore job, we just say what is the backup, what is the key space on the new cluster that we want to restore into, and then what is the universe, like the universe that we want to use. So as soon as we create the custom resource, we go in, like we schedule a restore job task in the operator in the backend, and then once it finishes, basically mark it as finished, and we can see on the right basically that the table will be the new table gets created on the right. So that was so that's mostly demo here. All of our CRDs
Aman, we might about 8 minutes past the end of the presentation. So we might want.
So basically, we'll just do quick, maybe a minute or so. So we have all of our CRDs have inbuilt documentation. This can be visualized using kubectl explain. We follow Kubernetes versioning, style versioning, and for our CRDs, and basically use conversion webhooks to transfer between versions if possible. And we talked about CEL already. For large shared clusters, we also support working with the vCluster project on Kubernetes, so you can have multiple copies of the CRDs in the same cluster. For developer testing, we run support running on Apple M1, M2 using Colima and on Minikube as well. For community members who are interested in trying out, we can go to the QR code or the link. The operator is currently in alpha stage. It is suited for experimentation and non-production use cases, but we are working on it and making it production very soon. So any contributions and feedback, we are active on the Yugabyte community Slack, as well as you can reach out to me or Sanketh or directly on the Slack as well. So for future work, we have to, we are trying to clean up some of the packaging for, use subcharts, working better with Red Hat OpenShift, adding some more features, support for mixed mode Kubernetes clusters as well. So yeah, thanks.
Cool. That was awesome. Thank you, Aman. think, yeah, so probably we can end here because we're already 9 minutes over time, but it was super useful, super interesting. So worth the time spent. Thank you.
Thank you. Thanks.
I think Prem says there might be a question here. Uh, are there any Linux operating systems not supported? Looks like your CentOS. Okay, so the question is, what Linux operating systems are supported by the operator?
So
Uh, yeah,
So
go
the
ahead.
operator works on will work on any of the, like, it works on Kubernetes, right? So we use internally an Alma 8 based container image for the operator, and same for the DB as well. So yeah, we are not using CentOS for any of our container images. If I understood the question correctly.
Yeah, I think that in Kubernetes, I guess we don't care about the operating system of the underlying node, and the container is
Yes.
bringing its own.
Yes.
Makes
Yes.
sense. Let me check. I think that's probably we can end it here. Yeah, sounds good. Thank you, Aman. Hopefully, we'll have future talks with. It was a little bit rushed, but we can have future talks with more details on the underlying implementation and different operations. How, like, I think, how does actually backup work? How does a rolling operation work, etc.
Yeah.
But
Yeah. Thank
yeah,
you. Yeah, we'll certainly schedule future talks about this. Thank you so much.